Welcome to Factory on Air by DBR77, where smart manufacturing gets real. This is episode 19, Value Stream Mapping and Machine Load Analysis. You can't optimize what you can't see. In this episode, we explore how combining live production data with dynamic value stream mapping helps factories identify bottlenecks, balance workloads, and streamline flow from order to delivery. You'll learn how DBR77 enables real-time simulation of layout changes, scheduling variants, and machine utilization, all visualized inside a digital twin of your factory. VSM isn't just static anymore, it's dynamic, data-driven, and ready for decision-making. Factory on Air is powered by DBR77, the platform that helps you see, simulate, and solve your production challenges in real time. Let's get started.
Welcome back to the Deep Dive. Today, we're getting into the heck of it, really into the heart of modern manufacturing. You know, if you're involved in production, you feel that constant pressure, don't you? You need to be flexible, handle custom stuff, be faster than the next guy.
And use everything you've got optimally.
Exactly. And the tough part is that the old ways, the spreadsheets, the static plans, they just don't cut it anymore, do they?
No, they really can't keep up. They give you a snapshot, maybe, but the factory floor, that's a moving target. That's always changing.
Constantly. And that constant change, that volatility, that's precisely what we're diving into today. We've looked at sources focusing on pulling together two really key tools, value stream mapping, VSM, and machine load analysis. But, and this is the crucial bit, we're looking at them through the lens of, well, dynamic real-time systems.
So not just looking back, but looking forward. Exactly. The mission here is to understand how, combining that detailed operational data, the stuff coming right off the machines, with really good simulation, how that turns these tools from just reports about the past into, well, predictive powerhouses.
Okay.
This deep dive, it's kind of your shortcut to seeing how you can unlock hidden production capacity. Moving beyond just observing what happened and getting into optimized, proactive action, predicting and planning.
Yeah, that shift from static analysis to predictive modeling, that feels like the absolute core of, well, staying competitive in manufacturing today. If you can model tomorrow's headaches today, you're ahead of the game.
Absolutely. You win.
So let's lay the groundwork. Section 1, VSM. It's not a brand new idea, is it?
Yeah.
But why is it still so vital? That first step for getting clarity on what's actually happening.
Right.
I've heard it described like an X-ray for your process.
Yeah.
It shows you the whole journey, right? From the customer's order all the way to the finished product heading out the door.
That X-ray analogy is actually pretty good because VSM forces you as an organization to see your operations not as separate islands, the production here, logistics there.
Right, the silos.
Exactly. It forces you to see it as one single system, a flow. And when you do it right, VSM lets you pinpoint and, crucially, measure the 4 big things holding back efficiency.
Okay, what are those 4?
First up, you identify stops or downtime. These are the obvious ones usually, places where work just stops. Big machine breakdown, you run out of materials, easy to see, often hard to fix without knowing the ripple effects.
Yeah, the big painful stops.
Then there are the things that slow you down even when everything seems to be running.
Okay.
So second, VSM finds the bottlenecks. These are your constraints. The points in the process that limit how much you can produce overall, no matter how fast the steps before or after it are running.
The narrow point in the pipe, essentially.
Precisely. It's a system limitation. Third, you uncover superfluous operations. These are the steps that take time, cost money, use people, use machines, but from the customer's point of view, they add 0 value.
Like moving parts back and forth unnecessarily, or maybe extra inspections.
Exactly. Moving stuff between stations that really ought to be next to each other, or having 3 different people check the same thing. It looks like work, feels like work, but it's just adding cost.
Your resource drain. Got it.
And finally, VSM helps you categorize pure waste. This is where you really separate the activities that genuinely create value from those that just consume resources without any benefit. Understanding this difference, quantifying how much of your total time is actually adding value, that's fundamental.
Right.
Without that clarity, trying to speed things up might just mean you're making your existing mistakes faster.
Yeah.
Which doesn't help anyone.
No, absolutely not. So it really is strategic. You stop guessing about where the problems are, where to invest, where maybe you can cut back, and you get this, evidence-based picture of your operations health.
An economic map, almost.
But, okay, this brings us to the big but, the challenge, which takes us into Section 2. Traditionally, VSM tells you what was. It's analysis, not really planning, right?
That's the inherent limitation, yes.
Yeah.
Traditional VSM is static. It's a map you draw based on data you collected, maybe over a couple of shifts last Tuesday.
Right, a snapshot in time.
Exactly. But if your factory is dealing with lots of different products or demand swings wildly, that map, it's out of date almost as soon as you finish drawing it.
Yeah.
A key machine breaks down unexpectedly, or suddenly everyone wants product B instead of product A. Your static map doesn't tell you the best way to handle that now.
Okay, so the obvious question is, how do you deal with that? That constant change, the chaos sometimes. How do we make VSM dynamic, make it live?
And the answer really lies in bringing simulation into the picture. That's the critical upgrade we mentioned.
Simulation, okay.
You basically take your VSM, your map, and you transport it into a dynamic virtual world. Think of it like creating a really detailed digital twin of your whole production process, maybe even logistics too.
A digital twin. I've heard that term a lot. So a virtual copy of the factory.
Essentially, yes. A high-fidelity virtual lab. And in this lab, you can run experiments, high-stakes experiments like, what if our main supplier is 3 days late? Or what if demand doubles overnight? You can test these things without risking actual inventory, without breaking real machines, without stopping the actual production line.
Okay, that's powerful. Risk-free testing.
Hugely powerful. This dynamic modeling lets you figure out the best way to operate under different conditions before you actually spend money or time changing things on the real floor.
So this digital twin idea, let's get specific. What kind of things can you actually test in this virtual factory? Beyond just will it go faster? What impacts cost and time?
Oh, you can get really practical. The sources talk about testing things like changes to the physical layout of the hall.
Moving machines around.
Yeah, but it's not just about tidiness, it's about flow. Simulation might show you something counterintuitive, like maybe moving machine X further away from machine Y actually helps overall.
Really? How?
Well, maybe that extra distance creates just enough buffer space naturally, so when machine X runs super fast for a bit, it doesn't immediately jam up machine Y. You wouldn't guess that, but the simulation shows it.
Interesting.
You can test different sequences of operations. Should we run all the big jobs first? Or maybe run the small, quick jobs to free up that bottleneck machine faster? Simulation tells you the impact on delivery times and cost.
So you can prove that maybe a weird-looking schedule is actually the most efficient one.
Absolutely. You can model varying work shifts. What's the real impact of switching from 3 8-hour shifts to 2 overlapping 10-hour shifts? You factor in the changeover times, the machine warm-ups.
Yeah.
The simulation calculates the true cost and throughput.
Okay.
And maybe most importantly for resilience, you can model operations in emergency or failure modes.
The what if it breaks
Right.
scenario.
Exactly. Machine A goes down for 4 hours. What happens? The simulation can automatically figure out the best way to reroute work, maybe use an alternative process to minimize the damage to your overall delivery schedule. It gives you a pre-calculated contingency plan, maybe even estimates the extra cost per unit.
So it's taking all that static VSM data, the distances, cycle times, setup times, and making it interactive, predictive.
Functional and predictive, yes. And critically, it's not someone manually updating a diagram once a month.
Right.
These advanced systems, they pull in real-time data from the factory floor, from sensors, from the MES system to keep that digital twin, that VSM map, constantly up to date. That's the dynamic part.
Okay, so it's always reflecting reality.
Very, very close to it.
Yep.
And this allows users to instantly model complex what-if scenarios. What if raw material costs jump 30% next quarter? How does that affect profitability if we keep the current schedule? What if we get a sudden huge order for that low-margin product we make?
Okay. You can analyze the impact on your key metrics. Throughput, overall costs, and maybe the most critical one for your customers. Realization time, how long it takes from order to delivery. Lead time, yeah.
It's really about having the sophisticated ability to ask what if and get a fast, accurate, data-driven answer almost immediately. Okay, but for that simulation, for that dynamic VSM to be accurate, it needs fuel, right? Good data. Which brings us nicely into Section 3, the engine room. Machine load analysis.
Mm-hmm.
This relies entirely on getting good real-time data straight from the source, doesn't it? We know data can come from sensors, from the manufacturing execution systems, MES, maybe ERP system.
Right, those are the main inputs.
But just knowing, say, that a machine was up for 90% of the shift, that's not enough for this kind of dynamic load modeling, is it? You need more detail.
Way more detail. General, high-level numbers hide too much. For accurate load analysis, you've got to dive deeper into metrics that often get, well, overlooked in standard reports.
Okay, like what? Well, obviously, you need the basic machine operating time. That's your baseline utilization. But far more critical, especially today, is accurately measuring changeover times.
Setup times between different products.
Exactly. Some sources might use specific terms like pre-Zebrogenia in factories making lots of different things, where machines might switch products several times a day. If you don't track that changeover time accurately, it kills your schedule's predictability. It's a silent efficiency killer.
Yeah, you think you have capacity, but half of it is eaten up by setups you didn't account for properly.
Precisely. You can't schedule reliably without knowing that lost time. But then there are the even sneakier costs. The death by 1,000 cuts, you might say.
Okay, what are those?
This is where we look at microstops. Again, you might see terms like micropristoti. These are the tiny, often completely unrecorded delays.
Like a quick jam, a sensor glitch, waiting a few seconds for an operator.
Exactly that. Things that last maybe only seconds, perhaps a minute. Individually, you barely notice them, but collectively, they can add up to hours of lost production time over a week or a month.
Wow.
Capacity you thought you had, just gone, evaporated due to these tiny systemic instabilities. And if your system relies on operators manually logging downtime, forget it. Those little stops almost never get recorded.
Okay, that brings up a big problem, doesn't it? If machine load analysis needs to capture these tiny microstops, how do you actually get that data reliably? Especially in older factories with, machines that aren't exactly state-of-the-art and maybe rely on manual logs. How can you trust the data feeding the digital twin?
That's a huge challenge. You're absolutely right. And it points to why you need sort of multi-layered data strategy. You can't just rely on one source. So the basic data from the MES tells you maybe which work order is running, who the operator is. The ERP gives you the bigger picture, the costs, the overall planning context. But to catch those critical microstops, you generally need real-time data capture. Often this means using specialized IoT sensors or maybe edge computing devices that you actually add onto older machines.
Retrofitting them.
Exactly, retrofitting. These devices can measure things directly, vibration, power draw, cycle counts, right at the hardware level. They bypass the need for manual input, bypass slow system updates, and feed that granular data straight into your analysis platform.
Ah, I see.
And this is how the system can accurately compare actual cycles versus planned cycles. It immediately flags when things aren't running to standard, maybe because of material issues, maybe the operator needs more training, maybe the machine itself is starting to drift out of spec.
So the IoT sensors give you the super detailed microscopic view. The MES gives the work context.
Yeah.
And the ERP gives the financial framework. Putting all that together gives you the full picture for machine load analysis. Precisely. And that comprehensive view lets the analysis achieve its main goal.
Balance.
Balance.
Yeah. Eliminating uneven work distribution across your machines. The analysis identifies machines that are consistently overloaded, running flat out all the time.
Which sounds good, but isn't.
Right, because it massively increases the risk of breakdown. Maintenance costs go up. And if that machine is the bottleneck, it stretches out your delivery times.
Okay.
At the same time, the analysis pinpoints machines that are underloaded, just sitting idle or barely working. That's wasted capital investment, poor resource allocation.
So you find the overworked and the underworked machines.
And then you can intelligently redistribute the work, balance the load across your existing assets. Maybe you don't need that new $500,000 machine the production manager is asking for. Maybe you just need to use the machines you already have more effectively.
Ah, okay. That's where the big financial argument comes in, isn't it? Optimizing existing assets instead of buying new ones.
That's often the most immediate and impactful win.
So what are the other sort of measurable strategic benefits you get from achieving this balanced load?
Well, the benefits stack up. You definitely get better resource utilization, like we said, which eases the pressure for new capital spending. That's huge. Secondly, you significantly reduce the risk of unexpected breakdowns and those frustratingly long lead times because you know which machines are running close to the edge and you can manage that proactively.
Right.
This directly leads to shorter cycle times overall and a measurable improvement in OE overall equipment effectiveness. You're cutting out that internal friction, those hidden losses.
Okay.
And strategically, the whole factory just becomes more flexible, more agile in its planning. If a huge unexpected order lands on your desk tomorrow, you can quickly run the analysis and know exactly how to reshuffle the existing workload based on the true current capacity of each machine to accommodate it. It enables a much faster, more confident response to changing customer demands.
Okay, this sounds very impressive in theory, the balance load, the flexibility, but we need some proof, right? Evidence that this kind of simulation and analysis actually delivers real results, not just nice-looking charts.
Absolutely. Theory is one thing, practice is another.
So let's move to section 4, real-world impact. What did the sources show in terms of quantifiable results?
Okay, the case studies really help make this concrete. Take the heating device producer, for example. By using dynamic VSM, running those simulations, they modeled different ways to handle inventory between steps.
Buffers. Right?
Buffer stores. And the simulation ultimately justified reducing the number of these intermediate buffers by a massive 35%.
35% reduction in buffer inventory. That's significant.
It's huge because less buffer means less cash tied up in inventory just sitting there. It means less complexity in moving stuff around. And it means the product flows through the factory much, much faster from start to finish.
Yeah, that often feels counterintuitive, doesn't it? People think more buffer equals more safety, but sometimes it just hides the real problems.
It often does. The simulation proved the buffers weren't helping. They were actually masking the true bottleneck, which was somewhere else entirely.
Interesting. Okay, what else?
Then there's the food processing plant. Their value stream simulation led them to do something pretty radical. They actually removed an entire packaging station, took it out, and as a direct result, they shortened their overall lead time by 20%.
Wow. So getting rid of equipment made them faster.
In this case, yes. The simulation showed that particular station wasn't really adding needed capacity. It was acting more like an unnecessary constraint, possibly adding complexity, maybe extra change over time. The simulation gave them the hard data to prove that, in their specific case, subtraction was addition. Removing it streamlined the flow.
That takes confidence, backed by data. And you mentioned one related directly to balancing the load, the automotive example.
Yeah, the automotive factory. That's a great case study because it directly links that detailed machine load data back to smarter scheduling.
How so?
Well, by analyzing the real second-by-second load on their machines, not just relying on standard times from a planning sheet, they could optimize which jobs were assigned to which machines and when. Really fine-tuning the assignments based on actual current capacity.
Okay.
And this intelligent redistribution of the workload, it resulted in a documented 15% increase in overall machine availability.
15% more uptime.
Essentially, yes.
Right.
15% more potential production time recovered just by making smarter decisions based on real data about where and when each job should run.
Okay, these examples are compelling. So for the listener out there who's thinking, right, I need this. How do they actually start? This sounds like a big undertaking, not something you do overnight. Is there a structured approach, a roadmap?
Definitely. It has to be structured, and it's crucial to see it as a cycle, not a one-time fix. Continuous improvement is key. The sources generally outline a kind of 6-step roadmap.
Okay, 6 steps. What's step 1? Step 1 is absolutely foundational. You have to map the current state. You need to thoroughly understand how materials and information flow right now, warts and all. You can't optimize a process you don't fully understand in its current imperfect form. Makes sense? Know where you are before you plan the journey. Step 2. Step 2 is about getting the fuel we talked about. You must collect operational data. This is where you leverage those systems, IoT sensors on machines, the MES tracking work orders, the ERP providing cost context. Getting clean, granular, reliable data is critical here. Okay, map the current state, collect the data. Step 3 must be finding the problems.
Exactly. Step 3 is identify the specific points of loss and downtime. Really drill down. Find those hidden microstops. Confirm where the chronic bottlenecks actually are. Use the data to pinpoint the pain points accurately.
Right. Diagnosis. Once you have that high-fidelity map of the current state, powered by good data, and you know where the problems lie, then you move into the predictive phase. Step 4, this is where the simulation magic happens. You model simulation variants, the what-if scenarios.
Precisely. You build and test your different ideas in the digital twin. What if we change the layout? What if we use different material handling? What if we alter the shift plan? You model these changes virtually.
This sounds like it could be the most time-consuming part, maybe. running all those models.
It can be intensive, yes, but think about the payoff. You're avoiding potentially very expensive mistakes in the real world by testing them virtually first. It buys down future risk significantly.
Good point. Okay, so after modeling comes evaluation.
Step 5, exactly. You evaluate the quantitative impact of those simulated changes. How does each variant affect your key metrics? Overall lead time, cost per unit, machine utilization. You compare the outcomes objectively.
And finally, step 6. Step 6 is where the rubber meets the road. You implement the best solution identified through simulation. And this is vital. You establish real-time monitoring. You need that continuous feedback loop to make sure the improvements stick, to keep the dynamic VSM current, and importantly, to cycle right back to step 1, ready to find the next area for improvement. It's continuous. Okay, that's a clear framework. Map, collect data, identify losses, model variants, evaluate, implement, and monitor. Rinse and repeat. But as we touched on earlier, getting there isn't always easy. There are hurdles. Let's spend our last main section, section 5, on those challenges. If the system needs good data, the biggest hurdle has got to be those data gaps, right? Especially in factories with older equipment.
Without a doubt. That's hurdle number 1 consistently. The old garbage in, garbage out principle applies perfectly here.
Right.
If the data you're feeding into your digital twin is incomplete, or inconsistent, or you just can't get it easily from certain legacy machines, then your simulation results, your predictions, they're going to be flawed from the get-go. And yeah, many factories worldwide still have a lot of older, reliable equipment that just wasn't built with modern sensors.
So what do? You don't necessarily want to scrap a perfectly good machine just because it can't easily share data.
No, absolutely not. And this is where the technology solutions have become quite clever. We mentioned retrofitting earlier.
Yeah, adding sensors.
Adding external sensors or edge devices is often the first step. They can measure key parameters directly, but sometimes even that isn't feasible or gives incomplete info. So the second part of the solution often involves using sophisticated pattern recognition algorithms within the dynamic VSM software itself.
Okay. How does that help?
These algorithms can look at the data you do have, identify patterns, correlate events, and intelligently estimate or impute the missing data points based on statistical probability. It's not perfect, but it's often much better than having a total black hole. The goal is always to get as close as possible to a continuous, real-time data flow, because like we said, static analysis just doesn't work when production is constantly changing.
Okay, so there are technical ways to tackle the data gaps, but you also mentioned it's not just about technology. There's a big organizational hurdle, too. This isn't just an IT project, is it?
Oh, absolutely not. And that's where many initiatives stumble. Even if the tech is great, we've seen it happen. For dynamic VSM to truly succeed, you need deep, sustained, cross-departmental involvement. It cannot live just within production or just within IT.
Who needs to be involved?
Well, you need production, obviously, to validate the process maps, understand the operational realities. You need planning involved to help define and test different scheduling scenarios, shift patterns. You need logistics to model the impact of material flow changes. And you definitely need IT to manage the data infrastructure, the integrations, the security.
So production, planning, logistics, IT, at a minimum.
At a minimum. If these groups stay in their traditional silos and don't collaborate closely on this, the whole thing will lack the necessary context and likely won't deliver the promised results. It requires a shift in thinking towards shared goals and shared data.
It really sounds like mastering this dynamic VSM and machine load analysis. It's almost like a foundational piece of a much bigger puzzle, isn't it? Part of that whole push towards digital transformation.
It absolutely is. It's often one of the most practical and impactful starting points for that larger journey. When you look at full-scale digital transformation across a big company, it gets incredibly complex. You need integrated tools, maybe a comprehensive company-wide strategy, sometimes called a digital development roadmap or DRD.
A DRD.
Yeah, a roadmap that lays out how all the pieces fit together, the dynamic VSM we've discussed, broader IoT data strategies, maybe robotics, integrating with finance systems for the CFO, across potentially many different factories or business units. It's complex. But if you can successfully implement and get value from dynamic VSM and machine load analysis in one area, you've basically proven you understand the core principles needed to tackle that bigger digital landscape. You've built the foundation.
That makes a lot of sense. Build capability, prove the value, then scale. Okay, that brings us towards wrapping up. Let's just synthesize the main strategic takeaway here. Why should manufacturers be prioritizing this approach, dynamic VSM, real-time machine load analysis right now?
Look, at the end of the day, this methodology is about building a more resilient, more efficient, future-proof manufacturing operation. It directly leads to better operational effectiveness because you're targeting specific identified weaknesses in your value stream, not just making general improvement.
Right, targeted action.
It fosters a much more balanced line operation, which reduces stress on people and machines, minimizes failure risk, and that inherently translates into lower production costs. You're systematically finding and eliminating waste, and you're making the absolute most of the expensive assets you already own.
So what does this all mean for you, the listener?
I think it means gaining the ability to scale your production effectively when demand grows, and, crucially, being able to adapt quickly when customer needs change or unexpected problems arise.
Mm-hmm.
If you can simulate that sudden 20% surge in orders and know instantly, okay, machine 7 and machine 12 will become bottlenecks and we'll need X hours of overtime on line 3, you're just operating on a completely different level than competitors who are guessing.
You're moving from reactive firefighting to proactive, data-driven control.
You're transforming, really, a traditional plant into something much more like a modern center of digital excellence.
Well put. And maybe on that thought, here's something final for you to consider this week. Okay, let's hear it. If you feel your current operations are already pretty good, yielding strong results, just ask yourself, how much hidden waste, the kind only revealed by tracking those tiny microstops or running dynamic simulations, might still be lurking in your processes? How much potential competitive advantage are you leaving on the table? And maybe more pointedly, what critical process, maybe your main production line or you're running today, that has never been put through a virtual stress test, never simulated against a major machine failure or a sudden supply chain disruption or that massive unexpected order? Are you flying blind on your resilience?
That's the question to ponder. How prepared are you, really?
Indeed. The thought of those micro stops alone adding up, that's definitely food for thought and perhaps a spur to action. Okay, that's all the time we have for this deep dive.
Thanks for tuning in.
We hope this has been valuable, and we look forward to exploring more insights with you next time on The Deep Dive.